Let's continue the introduction to generalized projection. As I mentioned on Tuesday, there are two constraints in all the algorithms, all the frog algorithms. We have gate constraint and the data constraint. And the initial case, of course, is usually none of both sets. But you can force the function to be satisfied with either gate or data constraint repeatedly, and hopefully the electric field will converge to the true solution, which is represented by the cross-section points between these two sets. Including the iterative Fourier transform algorithm we introduced in the lecture slides. It takes advantage of the concept of generalized projection. But the only difference is how to update the new electric field from the original or the previous gated signal. If you look at the flow chart, okay, it means the update from this one, the updated gated signal field to A of t, the new electric field. In the original iterative Fourier transform algorithm, we did it by a simple integration. As you have seen in the examples I showed you on Tuesday, sometimes, especially when the signal pulse is of multiple peaks, this simple operation does not work well. The frog error cannot keep on decreasing, and the convergence is usually very poor if you have multiple peaks. So there must be some other better methods that can be used for this process, okay, from A sig prime to A of t. Okay, now let's take a practical point of view, how to implement the algorithm numerically. Numerically, a continuous function A of t, which is the signal pulse field, is represented by a row vector. Okay? For example, the blue curve represents A of t. And how do you represent this continuous function in your program? Of course, you have to perform sampling. Okay? And it's easy. Say you sample the electric field function at n points. So you got A1, A2, all the way to A sub n. You got n data points. These data points are temporarily separated by a unit step dt. Okay? So A1 means this one, the original function A, when t equals the left boundary, which is minus big N times dt over 2. And the big N means the total number of sampling points. Okay. The middle one, which is here, when t equals 0, it should be A sub n over 2. Okay. And the last one is A sub n, which is A of when t equals big N times dt over 2. Okay. So this is a very simple implementation. After sampling, you got a row vector, 1 by n row vector, representing the vector big A represents A of t. And then similarly, we have gate pulse, right? G of t. You can do the same thing. So you got a row vector big G consisting of G1, G2, all the way to Gn with a similar approach. Okay? They share the common unit step size dt in this example. Okay. So now you have two vectors, big A and the big G. The next question is, how do we represent the frog trace, okay, numerically? Of course, it must be some matrix instead of just vectors, right? But how do we create the matrix to represent the frog trace? So we have to start with the gated signal because frog trace comes from the collection of many gated signals, right? So by definition, your gated signal A sub sig t when tau equals 0, a very special case, should be A of t times G of t, right? So the blue curve means A of t. The red dashed curve represents G of t, okay? So when tau equals 0, you should get a function which is the product between these two curves, A of t times G of t. And then numerically, it's equal to vector A dot cross vector G, okay? Dot cross means term-wise product, okay? So A1 times G1, the first element of vector A multiplied with the first element of vector G, okay? Similarly, A2 times G2 all the way to AN times GN. So this row vector means A sub sig when tau equals 0. Is it okay? How about the case when you have some non-zero delay? For example, the delay tau equals 1 unit step size dt. Okay? So if you check the continuous functions, A of t remains. The blue curve does not change. But the red curve has to be shifted to the right by 1 unit dt. Okay? So you have A of t times G of t minus dt. Okay? But what's the case numerically? The vector A remains, but this time you have to perform term-wise multiplication with respect to G sub 1. Okay? What is the meaning of G sub 1? It's defined here. Gn, G1 all the way to Gn minus 1. So this is the cyclic shift by 1 unit. Okay? It is still an 1 by n row vector. Okay? The number of elements does not change, still n elements. But the order is slightly changed. Okay? So the first element shifted to the second. Second element, G2, shifted to the right. Okay? And the last element has no way to shift, so go back to the first one. So that's the cyclic shift. And it's defined by G sub 1. Okay? So if you look at the figure, you can see the red curve has been shifted to the right by 1 unit. So now G1 temporarily aligned with A2, right? Gi sub 1 aligned with A sub I, and the G sub n minus 1 aligned with AN, and the G sub n is already beyond the range of time window. Okay, this is your time window. Originally, the temporal sampling is within this time window, but because of the shift, 1 data point is beyond the window. So you have to move Gn to the first element. That is the meaning of cyclic shift. Okay. And if it is okay, then you can generalize the idea to arbitrary delay. Say it's J times dt, J units of step size. So numerically, it can be represented by this. Vector A dot cross G sub J, the cyclic shift of G vector by J units. Okay, so if you can do that, you can you can generate the matrix representing A sub sig for arbitrary delay. Okay, so it's already closer to the Floch trace, right? What is the relation between Floch trace and A sub sig? Do you still remember? Floch trace is a frequency domain data set. To this point, this is only a time domain data set, right? So of course, you have to perform Fourier transform. And the Floch trace is related to power spectrum instead of complex spectrum. So you have to perform modulus square, absolute square. Okay, just 2 steps ahead. So this is what we should do. Say after the outer product, okay, A transpose cross G vector, you got an m by m matrix like this. And this is named outer product matrix. Okay? But there is no clear indication about the relation between this outer product matrix represented by O matrix, small o matrix, and the A sub sig. Okay? But can you observe the relation? Okay. A1, G1, A2, G1, AN, G1, the second column, A1, G2, A2, G2, AN, G2. Can you identify the relation between this matrix with the gated signal matrix as we introduced in this page? For example, where is this one? Delay equals 0 should be this one. And where is this vector? Right, you are right. Diagonal, right? You see, it's here in the diagonal. And for other delay, you should get some other off-diagonal elements and with some cyclic shift. Okay, so it's already there, but we need some rearrangement. Okay, to manipulate the matrix such that we can get A sub sig matrix. Here, for the purpose of introduction, I designate row 1, the first row of this outer product matrix by this symbol, R1. Okay? R means row, 1 means the first row vector. It's a 1 by n vector. And this is R2, the second row. This is Rn, the nth row, the last row. And numerically, we can perform cyclic shift of Ri, the ith row vector, okay, by this number of units, minus I minus 1 parenthesis. Okay? The meaning of minus means cyclic shift to the left. Positive means cyclic shift to the right. Okay, that's it. How many units? I minus 1. So it means each row vector is treated independently and the cyclic shifted by a different number of units. That's the meaning. Then we should get some new matrix, O sub S. S means shift. Okay? So when I equals 1, okay, according to the formula, you have 1 minus 1, which is 0. Okay? So the number of cyclic shift is 0 shift, no shift. So the new matrix, the first row of the new matrix is the same as the first row of the original matrix, no change. Okay. So you repeat A1, G1, A1, G2, A1, Gn. Okay. But when I equals 2, so you have to manipulate the second row, R2. According to the formula, 2 minus 1 equals 1, so you have to cyclic shift by minus 1 units. Okay? So the new second row vector, RS2, equals cyclic shift to the left by 1 unit of the original second row vector, R2. Okay? So this is the original R2 vector. If you shift it by -1 units, so A2G1 to the left and then nowhere, so go back to the last one. A2G2 move to the left, so you have A2G2 here, and so on. So this is the second row, and you can perform the cyclic shift row by row. Eventually you got this. This is a new matrix, O sub S, shifted version of the outer product matrix. Okay. After that, you have to check the column vectors. Okay. So performing manipulation row by row, but after that, observe the matrix column by column. Okay. So let's see what is the first column. You see A1, G1, A2, G2, AN, GN. So this is the tau equals 0. The original diagonal has been moved to the first column after the operation. Okay? And if you check the second column, you see it represents A sub sig when tau equals minus dt. Okay? So it's a delay when delay equals -1 unit. And the third one, not shown here, should be tau equals -2 dt, and the 3 dt, and the 4 dt, and so forth. But the last one, because of the cyclic feature, it equals, tau equals 1 dt, plus 1 dt. Okay. So although the order is not intuitive, but you know, after the manipulation, the matrix O sub S is already the gated signal matrix A sub sig. Every delay has been represented by different columns, column vectors. Okay? Any question? Good. But we need frog trace. Okay? So what can we do? As we have seen in last page, the columns of OS matrix represent gated poles A sub sig T tau. Like the first column means A sub sig when tau equals 0. So you can do column-wise DFT. DFT means discrete Fourier transform. Okay? So you can perform DFT for the first column. Then you can get this one, the red one, big A sub sig, omega tau. Okay? Because after Fourier transform, variable t becomes variable omega. So you move to the frequency domain. Tau variable does not change because the entire column vector means tau equals 0, even after Fourier transform. Okay? So mathematically, just performing DFT for C sub S1, the first column of OS matrix, you got big A sub sig when tau equals 0. And the column by column, you got a big A sub sig at different delays. Okay? So eventually you got a new matrix, big O sub S. Big O means in the frequency domain. Okay? And each column represents n by 1 vectors. So actually this is an n by n matrix. Okay? But what is the mathematical meaning of this matrix? Big A sub sig, which is the complex spectrum of the gated signal. It is still not the frog trace we can actually measure. But the only difference is a modulus square, right? This is frog trace, absolute square of big A. So all you have to do is this. After you got big O sub S, just perform element-wise modulus square. Each element taking an absolute square. You got this matrix, and it's already the frog trace. please.
What does modulus mean?
Modulus 就是 absolute value。OK， modulus square 就是 absolute square， 绝对值的意思。OK。Any other question? It's not difficult. It's just a numerical representation of what you have known already. Okay, but if you need to compose software program, it's necessary. You have to do that. Okay. Then the issue is how do we, after we know the numerical representations, how do we perform the algorithm? Okay. According to the first constraint, data constraint, you can replace the magnitudes. The second constraint, data constraint, you can replace the magnitudes of big O S matrix by the square root of the major Flock trace, right? Because you got the Flock trace data, and you must know the absolute square of the gated spectrum. Okay, that's for sure. So you have to perform the replacement. So that means your new big A sub 6 prime, a prime means updated. Okay, updated gated signal spectrum is just big O sub s with a prime. That means update. And for each element, you just perform the replacement according to your Flock data trace. Then you can perform column-wise inverse discrete Fourier transform for this matrix. So you go back to the time domain. Okay, and where is the step in the flow chart? Okay, let's go back to the flow chart. Where is the step? From here to here, right? 我们刚刚做到的是，我会表达了 complex gated spectrum 是 big O sub s matrix， 它在这个位置。接着你做了 data constraint， 这个东西的 phase 不变，留下来。这个东西的绝对值用 square root of Flock trace 取代。所以你得到一个新的 big O S prime matrix, which is here. Then inverse Fourier transform, going back to the time domain, you got the new small OS matrix, which is here. Okay, so the last step is how do we perform from here to here? That's the only step we need to go through, right?